Hello, my name is Gregory Goldston. Today, I'm going to be discussing how to model wave propagation through musical instruments, particularly the guitar and the pipe organ. Hopefully, we will be able to find the eigenvectors and eigenvalues of these wave equations to better generalize the solutions or find particular solutions given the constraints that were in the assignment. So, for both of these, we're going to be using the wave equation. The wave equation is a second-order partial differential equation, as you can see on the screen right here, that is used to describe the flow of both light waves and sound waves, or in our case, air waves, which is sound waves, basically. For our equation here, we're using the del squared operator on U, so we can, and we're saying that equal to 1 over the speed of sound squared times the partial differential of U, the second partial differential of U with respect to T. So, how does that work? Well, let's look at a guitar. So, with a guitar, we're going to have a certain length that our string's going to be, we'll call that L, and we're going to try and use the one-dimensional wave equation to solve how this air movement or how this string movement is modeled. So we'll start out with our equation as we listed before. We'll have the partial differential, the second partial differential of U, which is going to be our function of both one-dimensional space and one-dimensional time. So we have that with space there, and that's going to be set equal to, again, 1 over the speed of sound squared times the partial differential time, the second partial differential time. You think I'll pick that up right now? We know that a string is going to be anchored on both ends like a guitar. You can adjust the guitar string, however, that's never actually done while playing except for tuning reasons. So unless we were to focus particularly on that condition, we're just going to say that the ends are clamped down right now. We're going to say that there's going to be some, at time 0, there's going to be some function relating to how the string is going to be moving at the endpoints. We're going to have some displaced position at 0, and we're going to have some potentially initial velocity at time 0. So, in order to solve this, we're going to have to use separation of variables to separate our function u of x and t into a function purely of the spatial component x and a function of the purely temporal component t, and then we multiply by each other. Setting up this equation to solve, we will get the second partial derivative of x over x will be equal to 1 over the speed of sound squared times the second partial differential of t over t, which is going to equal some constant lambda, or we'll put negative lambda in this case. This is kind of nice. This is already kind of hinting at the eigenvalues that we're looking for, but we're not quite there yet. So, let's get on to the next part. Here we have our two important equations we're going to need. We're going to have the, because this is going to help us find our eigenvalues. So we have the second partial differential of x is going to be equal to negative lambda times x, and a very similar story with t, only our constant has c squared thrown in there, so it's a little bit different. We're going to have to change our boundary conditions up a little bit because the first one's just going to be, or both of our boundary conditions that we listed out before are going to be with respect to x and only influenced by the spatial component. So we're just going to have to use that. You can see it right there on the left side. And for our initial conditions, I think we're just going to have to keep it the same. We're not going to really deviate into that right now, and you'll see why later. So I want to discuss something else before we get into actually solving this, because there's another way to solve this that's useful, but not quite for what we're looking for. So let's go into D'Alembert's solution. So while we could solve these names via his equation, it wouldn't be the most straightforward way to find the eigenvalues and the eigenvectors. So like we're planning to do in a few minutes, we're going to take this case by case. However, I did want to point out this method of solving it because in some cases this is very useful. So the first thing we actually have to do is perform a change of variables, which is very similar to a change of coordinates. We will set our new variable w equal to x plus the speed of sound times t, and our new component z equals x minus the speed of sound times t. We can set this up to solve for our function equation, which I listed over here. And we are finding what each partial derivative of x is going to be equal to. So the partial derivative of x with respect to, the partial derivative of u with respect to x is going to equal the partial derivative of u bar over partial with respect to w times the partial derivative of w with respect to x plus the partial derivative of u bar with respect to z times the partial derivative of z with respect to x, and that simplifies to the partial derivative of u bar over with respect to w plus the partial derivative of u bar with respect to z. Now, the reason we're using u bar is because we switched our coordinates. So u was a function of x and t. We're going to call u bar a function of w and z, as you can see in there. That's important to note. We don't want to mess that up. So, process for the partial derivative of u with respect to t is quite similar. And by doing this chain rule that we just showed before and substituting as needed into the one-dimensional wave equation, we find that the second partial derivative of u bar over with respect to x and z is equal to 0. So one time it's taken with partial derivative of x, the other time it's taken with partial derivative of z. Now, we can actually solve this if we integrate. We can integrate with respect to z or w first. It doesn't matter which one. And we'll integrate with respect to the error as long as each function is purely a function of z and w for each integration. The results yield a very, very nice result. We can kind of get rid of our partial differential equations entirely and just say, all right, our function u of x and t is equal to some arbitrary function f of x plus ct plus some arbitrary function g of x minus ct. This is great for solving the equation. This is great for trying to figure out how this guitar can propagate, like if you have specific functions that you can plug in much easier. The problem with this is it doesn't actually give us what we're looking for in this case. So, on to what we have been waiting for. So, as I said, we're going to take this case by case. Let's do the case where lambda is greater than 0. So we'll go back to substitution of variables now. In order to make this easy to solve, let's substitute our lambda for any value of n is going to equal a squared for n. That just makes working out the second order partial differential equation a lot easier. We're going to say a sub n is equal to pi n over L. This will come in handy when we are getting into the Fourier part of it. And we are going to say that we are going to use that x solve. We are going to use the same sort of process when we solve for x. You see how this results in x double prime, the second partial derivative of x equal to negative a squared n times x. Well, I flip-flopped it a little bit, but the xn at the top is the solution to that equation given our initial condition, which was, if we go back here, there we go, x sub 0 equals 0. So how does that work? Well, let's try and solve for t now. So using our knowledge of second-order differential equations, we can use the same process to solve for t, which gives us t to the n equals some constant times e raised to the n at over LC plus the second constant times e raised to the negative. That should be negative there. Negative n at over LC. So how does that help? Well, we can use Euler's identity after that to get t to the n equals some constant times the cosine of n pi t over LC plus d sub n times sine of n pi t over LC. This is where it gets a little bit difficult because of how our initial conditions work. So we can't exactly say what the position is at time t. We could nail that down, but we don't know how far the string is plucked necessarily. So we can't say, well, at this point, at this part of the string, you know, at time 0, we're basically saying u of 0 sub 0 gives us 0, which is not what we're looking for. We could say that the partial differential of t at time 0 is going to be 0. And this is, it limits things a little bit, but it helps us solve the equation because it's kind of saying, okay, well, there's going to be no initial velocity. So you're assuming that this thing is released right at time 0 and it wasn't propagating before. And that's okay. And that's what we're going to use. So this allows us to infer that our constant d of n equals 0 because if we take the derivative of Tn, we're going to find that when we plug in 0, we get the whole cosine thing, which becomes sine is going to be 0, and we find that dn has to be 0. So we're going to find that t of n is going to be equal to c of n times the cosine of n pi t LC. So let's keep going. We combine our solutions for the part t and part x. We're going to get that u of x sub t equals, as we showed before, how we broke it up into separation of variables. And we're going to combine our x solution from back here. You'll see it right at the top right middle-ish. And that's what we're going to use to multiply times our function t. So let's try the case where lambda equals 0. We can solve this equation. You get nothing particularly interesting. We get second derivative of x is 0, second derivative of t is 0, leads to very not necessarily trivial solutions, but pretty close to it. And our final result is that u naught of x and t is going to be equal to 1. So this one we actually can't solve. You heard me right. X double prime is going to be equal to lambda x. This doesn't have any solutions by any standard means that we know. It does show us that the eigenvalues are strictly non-negative, which is kind of nice. So let's move on. Let's put it all together. Let's put our summation together. We'll say u of x sub t is going to be equal to a naught over 2 plus the summation from n goes to 1 to infinity of some constant a n times cosine of n pi t over LC times the cosine of n pi x over L. So we have two variables in here. Let's get rid of one of them. Plugging our initial condition of u of x sub 0 equals our f of x function. We don't know what that is, but it's some function. And f of x is going to be equal to a naught over 2 plus the summation of n goes to 1 to infinity of some constant a n times the cosine of n pi x over L. And this is kind of nice. Now we have everything in terms of x, which is, you know, awesome. Now we just need to get the Fourier cosine expansion. It's going to be an even one because we're working with cosines and strictly cosines here, to find our missing coefficients. So there we go. Ta-da! This is going to be for a naught using how we know to use, using Fourier cosine expansion, and each an is going to be very similar, 1 over 2 times the length of whatever the string is integrated from 0 to the end of the length of the string. That's going to be for whatever our function of f(x) times the cosine of n pi x over L, the length of the string, and dx. So how does that help us? What can we figure out from this? It's not perfectly precise. We could kind of treat each n as a harmonic and use that to kind of somewhat find a length to the guitar string to reach 440 hertz. Now, 440 hertz is notoriously the fourth A on a piano, or 432 if you're one of those people. But the whole point is that, yes, this is actually a frequency that kind of exists, and you can kind of try to find the length if you wanted to, just knowing this frequency. Let's use our method. So we'll use our simple frequency equation, which is saying that the wavelength is going to be equal to the velocity of the wavelength over the frequency of the wavelength. We're also going to say that our length is going to be 1 over whatever our harmonic is plus 1 times the wavelength. And the reason we do n plus 1 is because we are starting at n equals 1, and this typically is only a rule of thumb when you're getting into the bottom part with the harmonic being 2 or higher. So although we could maybe do theoretically 1 over 1, as far as a real world examples is concerned, it's probably best to do 1 over n plus 1. So v over f is the speed of sound at 343 meters per second. It's going to be divided by our frequency, yielding a wavelength of 0.7795 meters This is going to be used to find L now for any value of n, as we shown in our equation before. This is rudimentary. This does not take into account how the wave diminishes over time when you pluck a guitar string, yet keeps the same frequency. However, this is a good kind of a conclusion or some sort of real world example we can somewhat derive from this. So let's go to the pipe organ. Pipe organ is going to be a bit trickier. We were given an equation to depict one-dimensional wave flow, basically used for the pressure in the organ. So if you can picture like pancaking on top of each other and compressing and expanding at certain points. The best way to do this would be with a two-dimensional wave equation in cylindrical coordinates. That way you could calculate the pressures at a certain point rather than just assuming each disk is equally pressured across or each wavelength, each little pancake. However, this is what we're given to work with, so we're going to give this a shot right now. It's very similar to the other one that we did. We've got the partial derivative of p with respect, the second partial derivative of p with respect to x minus 1 over the speed of sound squared times the partial derivative of p with respect, the second partial derivative of p with respect to t is going to be equal to 0. We can rearrange this to pretty much use what we had with the guitar before. We'll assume the pipe is closed at the bottom for this example, and let's say it's closed at the top. So our respective boundary conditions would be as shown. So what can we do? Once again, we'll use the separation of variables technique. We can break up our function of p of x and t into p of x and t equals some function of x times some function of t. We'll go through the same little routine we did with the guitar, where we have the second partial derivative of x over x equals 1 over the speed of sound squared times the second partial derivative of t over t equals some lambda. So this is going to give us the same equations we got for the guitar. Our initial conditions are a little bit different though, and that's why I left it out at this point. So let's get into that. So just like before, we have our equations of lambda sub n is going to equal a. We're going to make the same substitution, and we're going to make that same substitution for a later when we get into the Fourier series. But for now, let's use our boundary condition to solve for x, which I talked about before, but now let's show the steps. So we're going to say that our solution is x equals some constant times cosine of ax plus b times the sine of ax. That's going to solve this equation on the left here. The second partial derivative of x equals negative lambda x. So we'll take the partial derivative of that, or just take the derivative of it. You know, there's only one variable we're dealing with here. So we'll find that. We'll plug in our initial condition, and voila. X is going to be equal to some constant a, we'll call it a, times the cosine of ax. Thus, p of x and t equals c of n times the cosine of n pi t LC over the cosine of a and x. Now, the cosine of a and x, we just combined our constants together to make c of n. Where did we get the other one? Well, the other one's actually the same identical process as what we did for x. I'm sorry, that is not the back button. It is the same identical process that we did for the guitar when solving for the temporal function. So we simply used that same result, plugged it in, and that's what we got. Just like last time, our case at lambda equals 0 is going to be p naught of x and t is going to be equal to 1, and lambda negative numbers is not going to be existing. So let's put it all together and see what we can get. Just like last time, we'll put this into the summation. We'll just say p of x and t equals a naught over 2 plus the summation of n goes to 1 to infinity of some constant a n times cosine of n pi t LC times cosine of n pi x over L. Once again, let's get this into one variable. So we'll plug in our initial condition. We're going to get out a f of x equals a naught over 2 plus the sum as n goes to 1 to infinity of some constant a n times the cosine of n pi x over L. And just like last time, we get pretty much the same Fourier equations as before. What does this mean for the pipe organ exactly? Well, this is a little bit different because now we're working with the movement of air pressure. We can't use our same formula to find exactly what the ideal length of the pipe organ would be. And honestly, this is where I kind of got stuck. Yeah, that was something I couldn't figure out on my own. Any questions, comments, or any ways that you can try and help solve this, that would be very much appreciated because this has been such a wonderful project to put together. I really would like to know how to do this. Thank you so much. And yeah, that's it.